All right, so for this morning's lab, we're going to be working with operator overloading and also copying objects and object copying semantics. So first off, what is an operator in C++? Well, an operator is just sort of the infix symbol, the plus operators, multiplication operators. It's basically using a symbolic representation of functionality as opposed to using an actual function. And in C++, sort of you have this expression here, 5 plus y, that's sort of the same as saying operator plus and calling that function on 5 and y. And so in C++, there's a large number of operators. There's arithmetic operators, there's assignment operators, increasing and decreasing, equality operators, logical operators, conditional, bitwise operators, etc. And so most of these operators can actually be overloaded. So you can make specialized versions of these operators that would act on your particular classes. There are some limitations, and Wikipedia has a relatively decent list of the different operators and details about them. And as I said, overloading these operators allows them to be used with different classes, your own particular classes that you've created, as opposed to the default classes. For example, if you wanted to make a fraction class, there is no fraction class in C++, but if you wanted to have that functionality, you could create one and then use the overloaded operators to act upon it similar to other numbers. The one limitation you want to think about when you're doing operator overloading is the fact that you want the operators to make sense. For example, you can make the plus sign operator perform multiplication or a square root or do various other things. C++, the compiler is not going to prohibit you from doing that sort of changing to the meaning of the plus sign operator, but it's not something that you should be doing. It should make sense in context. Question? As I mentioned, so a fraction class. So what would a fraction class, if you wanted to make a fraction class, look like? Well, you'd have an integer for the numerator and an integer for the denominator, and you store that as a private member variable. And then you'd have your public interface. So you construct it with the numerator and denominator. You'd have accessors so you can get the two numbers. And then you'd probably have some sort of conversion function where you'd say, OK, I'd take this fraction and make it a real value. But acting on that, we'd really want to be able to use this fraction class as we would with a real number. So with a real number, you'd be able to declare your variables. And then you'd make other variables like you sum. It's like x plus y, product x times y. That's very straightforward. But if we didn't have operator overloading, it would be rather difficult to act on that. So what you would have to do if we didn't have operator overloading is you'd have to have free functions. For example, fraction sum, x comma y, as opposed to x plus y, or fraction product. Or maybe you could do member functions. So x sum y or x product y. What we'd really want to be able to do is we would just want to be able to say, fraction x, fraction y, x plus y, and get a fraction out of that operation. So by default, C++ won't be able to do this. We'd have to actually define what we mean when we say we're adding two fractions. And so the way we do that is by operator overloading. And you're using the operator, use the keyword operator plus the symbol, and this sort of defines what happens for that operator. And so there's two ways to do that. You can do it in a non-member function where you specify, so for example, operator plus, and you have the left-hand side and the right-hand side passed in as parameters. Or you could do a member operator overloading where the left-hand side is the object of which this is a member function, and then you have the right-hand side on the other side. And so this actually sort of parallels what the signature of this sort of parallels what you would see if you actually had a normal function that you have a name with a regular calling syntax. So for example, here you'd have fraction sum, and x dot sum y, and you have, it's the same sort of signature here. And the implementation is the same, where you'd have, fraction, fraction, sum, and the two, the two variables. And then again, the member, if you have a member function, you have the you implicitly operate on one that you're a member of, and then the other one is passed in as a parameter. And then, so we use this a lot in different places in Rosetta. For example, in the XYZ vector class, which if you remember from previous lectures, is a class that represents a three-dimensional point in space. And when you do working with three-dimensional points in space, you can add, subtract, and represent them as sort of vectors operations. And you can use the notation. For example, here, this is the assignment equals operator. And so if you wanted to multiply an XYZ point, so a vector, multiply it by a scalar factor. So you have your scalar factor here, and then you just multiply in place each of the x, y, and z by that scalar factor, and return a reference to the object that you're operating on. Yes. And so then you'd use it like this, where you have, for example, you have a 111, 0.111 is an XYZ vector, and then you multiply it by a scalar factor, and then once that happens, you would then go and have the XYZ vector x being 333, as you would expect from scalar multiplication of vectors. I guess on one point here is why do we return this in this function signature? And that's just because of the way the operators, the multiplication equals operator works in C++. So the way that works with normal numbers, integers, reals, etc., is the fact that you multiply the variable that's on the left-hand side by the number that's on the right, and then this entire expression is equal to what happens for the left-hand side. So you can write expressions like this, where you have x multiplication equals 3 as an entire expression, and then use it further in the way. It's just it's the way that it's the way that C++ handles this assignment operator, and then because that's the semantics of the C++ operator, we should copy that in when we do the operator overloading. All right, so there are some limitations to operator overloading in C++. You can't create new operators, so you can't combine symbols or add additional symbols to the working set to make new operators. You have to stick with the set of operators that C++ provides. There's also a limitation on certain operators that you can't overload. Many of the common operators can be overloaded, but some of the more specialized operators for specific functions can't be. And for certain operators, the overloading changes the fundamental behavior. For example, if you try and overload the logical and the logical or, on the primitive types, these have short-circuiting behavior, so it doesn't necessarily evaluate every term in the long expression. But if these get overloaded, it may lose the short-circuiting behavior. The other thing is you can't change the arity of an operator, so the number of arguments that it takes. So if a certain operator takes 2 arguments, with the overloaded operators also has to take those 2 arguments. The one thing that you can do is you can change the signature of an operator, and by signature here I'm talking about both what it's sort of expecting and what it's returning. That is possible, but again, you really shouldn't. You should have it make sense in context with the rest of the operators in C++. Okay, so some common operator signatures. So for member access, you have the dereferencing operators and the indirection operators. These can be overloaded, and in fact, this is what we use in the Rosetta in the owning pointer classes. So an owning pointer is a regular C++ class, and by overloading the indirection operators and the dereferencing operators, we can then make it act like a pointer and use the same sort of syntax for pointer referencing and dereferencing. Likewise, you can also use the square bracket for element indexing, and with this you could make container classes that will take an index or some sort of keyword and make it work like a map or a vector. You can also overload the calling operator, the two parentheses, and you can use this to make it act like a function. You can make an object act like a function. And we use this in Rosetta for the score function object. And you've probably seen this already, where you can take a score function, and instead of calling some member function on the score function to score a pose, you can directly use this calling operator syntax to apply a score function to a pose. Again, you're still calling a function on a member function for the score function, but you're calling the operator call function instead of any sort of named function. Other operators are the arithmetic operators, and so these have this sort of signature. So addition, subtraction, multiplication, some of the bitwise operators. There's also unary operators for negation and bitwise negation. Logical operators, you can redefine equality, less than, greater than, etc. And redefining these logical operators is very useful when you're using container classes. For example, some of the container classes you want to do sorting, or they would need to have a total ordering of elements. So you would need to know, in order to search the container, which element is less than another element. And by overloading the less than operator, you can then use your new class in these containers. And so the container can then tell which object of your particular type is less than another object, and therefore it would be able to go through and appropriately sort the objects in the container, even though when the container was written, it had no clue about your particular derived type. There's also the negation operator, the exclamation point, and this is useful to make your class a logical value. So this can be used when, just in an if statement to give your class defines true-false semantics, even though it might have a more complex internal state than just simply true or false. There's also the shift operator, so these double arrows. So you've probably seen these a lot with stream operations, so outputting values, inputting values. In C, these are strictly used for the bit shift operators, but they have been overloaded in C++ to also work for stream operations. And I guess this is one of those points where we say, you should keep the semantics of the operator. And actually, if you look at people's complaints about C++ online, this is one of the things people complain about about operator overloading, is the fact that you have this confusion here in the shift operator. Does this operator mean a bit shift operation, or does it mean an output to a stream? And then there's some confusion about that, and it's one of the points of contention about operator overloading. And one of the reasons why, when you overload operators, you should be cognizant of the fact that you need to make them consistent with the semantics that already exist. Yeah. Oh, so is overloading that shift operator how the fold tree outputs the edges? And yes, so if you're using it in a stream context, like cout, arrow, arrow, fold tree, this would be the way it would do it, and this was how you do it. So in Rosetta, we do mostly use the shift operators, these two operators for input and output, because bit shifting isn't really something that we need to do in Rosetta. And And one of the limitations, of course, is I mentioned that there's the two different forms of operator overloading. So you can either have it be a free function or you could be a member function. So one of the limitations of the member function is the left-hand side has to be the object of which it's a member. And since when you're doing output to a stream, the left-hand side is always the stream. Since we can't overload anything or add any methods to the stream, the shift operator has to be overloaded as a free function. And so this is what the sort of the signature you would see very commonly is that you would have standard OStream reference. So you would return a reference to the standard OStream so that you can do that chaining. So the multiple output operators on the same line. And then the operator, and then as a free function, you would take the two variables, the left-hand side, which is the standard OStream, as a reference. Again, this is very important that you have a reference as opposed to trying to make a copy of the OStream, which doesn't work very well. I can say that's from experience. The compiler will complain at you a lot. And then whatever object that you're interested in doing an output or making an output function for. And again, this would be pretty much any object. And then as an implementation, because this is a free function, you don't have access to a lot of the private member variables. So it's somewhat difficult sometimes to make a good output formatting when you don't have the access to the internal state. So instead of trying to write the details about how to output in the actual function itself, a lot of times what we do is we make a show method in the object. So the show method is a member function of the object that you're trying to output. It therefore has access to the private variables. So we call the show function on the output stream, and then this would take care of outputting all the details about the private member data of the object. So this is a very common signature that you'll see. So you'll have, you'll have your class definition, and then at the bottom of the header file, you'll have something like this. All right. So there's also other operators, for example, the Inplace arithmetic operators. And so again, there's multiple operators that you can have here. And again, in the signature, one important thing with the Inplace arithmetic operators is the fact that you want to take a reference to your object because you're going to be modifying the object in place. And it also it can't be a constant reference. And then as a final note, you can also overload the assignment operator. So if you have just the plain equals operator, this can be overloaded as well. And that's actually very important. And so that's sort of what I'm going to talk about next, and what the point of the lab today is going to be mainly focusing on, is the fact that is object copying and object copying semantics. So this operation, and so this is actually calls an operator. So you have y, and you're assigning it to x. And what this means is you copy the context of y into the already existing variable x. This is different from the copy constructor here. So since you're adding this type name, this has a different meaning. So you're making a completely new variable foo of type foo named x, and then you're actually creating a new foo based on the contents of y. And so these are related, but they're different, handled differently in C++ because of the difference, the fact that you have an already existing object here, and you're creating a completely new object here. And this has been mentioned before, but I'll repeat it for thoroughness' sake. This syntax here, even though you have the equalities equal sign here, so it sort of looks like an assignment operator, internally this is handled exactly the same as the copy constructor case. So there's really no difference between these two semantics. Again, you're making a new object and initializing it with the values that you find in the y object. An important thing to realize about all of these cases is the fact that even if you don't specify a copy constructor or an assignment operator in your class definition, the C++ compiler will make one automatically for you because these semantics are very important when operating in C++. It sort of needs to have these available. But the one that the compiler makes is very simple. It just copies each and every private member variable as is, with not a lot of sophistication. The problem with this is the fact that if you have more complex data, for example, if you have pointers to objects, it's just going to copy the pointers. It's not necessarily going to do more complex copying of what's being pointed to. And so here we're going to talk about the distinction between shallow copying and deep copying. So here's, by default, the copy constructor and assignment operators will do shallow copying. And so here we have a class residue store. When we create it, we make a new residue. We store it in the residue OP private member variable, and we have some function that we can modify the residue for. And so we have a very simple main program. So we create a residue store foo. So we have foo. It contains a residue variable, and that, because of the creator, will point to a residue object. So in the next line, we invoke the copy constructor to make bar, copying from the value of foo. Since we didn't specify a copy constructor here, the C++ compiler will make a default one for us that will just simply copy the private member data. And it does a very simple copy, and it just basically copies the residue OP. So we have a copy of the residue OP, so residue gets copied, but what it's pointing to doesn't get copied. So now we have the foo variable contains the residue OP variable, and it's pointing to a residue that's on the heap. The bar, it gets its own copy of the residue OP object, but that's still pointing to the same residue object on the heap. So now we have foo and bar, and they're sharing the same residue. So when we go and we modify the residue object through foo, we also see the same modification if we access it through bar. This may or may not be what we want. So if we wanted to have a separate residue for each object, what we'd want to do is we'd want to make a deep copy. And so here, because the default copy constructor and assignment operators make shallow copies, we'd have to make our own versions of these in the class. And so the class gets a little bit more complex. So we still have the same modify and default constructors, but now we make a copy constructor. And a copy constructor is similar to the default constructor, except it takes a constant reference to the object that we're going to be copying. And now here, since we're making a deep copy, what we want to do is, instead of just copying the residue OP object, we want to make a copy of what's being pointed to. And so we make a new residue on the heap, and we invoke the copy constructor for the residue to make a copy of this residue that we're pointing to, and then store that. Similarly for the operator, the assignment operator. Again, we also copy the residue that we're storing. And so now when we go through the program, we create a new foo residue store, as before. But now when we make a copy via the copy constructor, we have the new bar variable, we have a new residue variable, but instead of pointing to the same residue object, we now have a copy of that residue object. And so when we modify through foo, we have the modified through foo, but bar keeps the old version of the residue. And so now we've separated out this residue object that's pointed to via foo and the one that's pointed to via bar. And depending on what we're doing, this may be more along the lines of what we want. Something that I sort of glossed over quickly, but I think is worth pointing out, is here in the assignment operator, you notice that there's this if check to say if this is not equal to source. So this is one of the things that you have to be aware of when you're overloading the assignment operator, is the fact that you can and actually will encounter instances where someone will try and assign an object to itself. Sometimes when you do that, that's fine. You don't necessarily have to be, it'll work fine. But one of the things that you have to be aware of is when you overload your assignment operator, you might get into a situation where if you're modifying, this, and you're modifying, it might make things inconsistent, the state inconsistent, if you assume that, the source is not going to be changing underneath you while you're changing yourself. If both sides of the assignment operator point to the same object, both of them are going to be changing as you change the object. And so that's one thing to be aware of, and it's relatively easy to put a check at the very beginning to say, am I assigning to myself? If not, if I am, I don't have to do anything. If not, then I can proceed normally.
Just a brief point on this. There's just a small typo on this slide where you're comparing the dereference value of this to the source. What you want to do is instead compare this pointer to the address of the source. So
right.
Instead of having a star on the left-hand side by this, you're going to have an ampersand on the right side by source.
Okay. Yeah. So I think Andrew's point is a good one. This is comparing the value of the two as opposed to the identity. What you want to do is you want to actually compare the pointers, so more identity comparison. So lose the asterisk and then compare this pointer is whether that's equal to, and then you use the ampersand operator to get the address of source. So you're comparing the memory location of the two objects to actually do object identity as opposed to a value identity as this is written. So, yeah, that's a good point. All right, so we have shallow copies, we have deep copies. What's the difference? Why would you use one versus the other? And both are useful, but it kind of depends on what you mean by your object. What sort of use case are you using it? So when you have a deep copy of your member variables, what you're really saying is that member variable belongs to this class instance. It's my object. I can potentially modify it at will, and I don't care. No one else is going to see it, so I can do whatever I want to it. And also more importantly, no one else should touch it. And if you do the deep copy semantics properly, this is actually, the others shouldn't touch it, is actually enforced by the compiler. You have this private member variable, and then only you can have access to it, and no one's going to change it or modify it without you knowing about it. A shallow copy, on the other hand, is good in those instances where you have a shared object. It's all right if multiple classes have access to it. In this sort of situation, you say, I'm not going to modify it gratuitously. I may make changes to it, but I'm only going to make changes to it that I think everyone else who could potentially have access to this would also appreciate having. And the other thing you're saying is the fact that if someone else makes changes to this object, I want to be informed of those changes. I'm good with the other people who have access to this making changes to this, and I want to track those changes. So as an aside, so the question arises, well, if you don't want modifications to be made to an object, why can't you just store it as a constant owning pointer? And this is in the deep copy instance. The point to make is the fact that just because you're storing something as a constant owning pointer, that just means that you can't modify it. It doesn't mean that someone else who might have just a regular owning pointer, they might be able to make a modification. So even if you have a constant owning pointer to an object, if you didn't implement deep copy semantics, someone else may be modifying that object. So that object, even if you have a constant owning pointer, that what you're pointing to might change underneath you. All right. So in the deep copy semantics, we want our own object, but why store a pointer to that object? Why not just store the object directly and then just have the default, the default copy constructor and assignment operator? When it makes a copy, it'll make our copy for us. Well, the reason for that has to do with the includes. So include is actually, it's a preprocessor statement. So this is slightly different. So in C compilation, there's sort of two steps. There's the preprocessor acts on the file, and then the C compiler acts on the file. And so these sort of directives, so the hash sign, the pound sign, the defines, the includes, the macros, et cetera, those are preprocessor directives. And so these aren't parsed by the compiler itself, they're parsed by the preprocessor. And the preprocessor has only a very limited knowledge of C++. So it does, when it does the include, it does a very simple text-based replacement. So basically what it does is it takes this include, it finds the file that you're including, and it just substitutes this include line for the entire contents of the file. So the entire contents of the file you're including are basically copied into the file that it's being included from. And this happens recursively. So here's an example. Here's the protocols design op greedy opt mutation mover, and here's a section from the top of the file showing your include. So we have this nice long include list. So the preprocessor goes along and it sees, okay, here's an include file. So what it does is it removes this line and then substitutes the contents of the greedy opt mutation mover header file, which is a portion of which isn't listed here. All right. Well, now the preprocessor works recursively. So it goes through this file and it finds another line. For example, we'll move down to the mover line here. So it includes the mover.hh file. And so here's portions of the text of the mover.hh file. All right, let's go again. We have the pose.hh file. Now it takes this line and replaces this line with the contents of the pose.hh file. And now we have more headers. And now we replace the contents of the core chemical atom icord HH line with the context of that header file. Yes?
So can adding just one include line make it so it takes a really long time to compile your new?
Yeah, that's exactly the case. So if you had, the more headers you have, yeah, I guess I should point out also that we've just gone through sort of one layer. Remember that there's all of these other includes that we've sort of bypassed. And so yeah, so by adding additional headers to a file, you can greatly increase the time that it takes to compile. And that's one of the key limits, the reasons why we prefer to use pointers as member variables, which I'll get to in a second. Yes?
Would there be any situation where the order of the includes would matter? I mean, as long as they're in the beginning of the CC file as multiple, right? Or like header file.
Right. Does the order of the includes matter? Yes, the order of the includes matters because it does substitute in the order that it happens, but you're also right in the fact that because we typically put the includes all at the front, if you have all the includes prior to anything you define, all of those includes will get included even in the order. Yeah, there's a little bit of a limitation as far as things like if you have circular includes, like if you have one file that includes another file, things can get a little bit iffy. We've talked about header guards earlier. That's very important regarding circular includes, and also it also helps limit the combinatorial explosion.
Does this suggest that they can hang just on going to a loop of includes somehow?
Yes, so if you have can it hang with includes? Yes, if you have a circular include, if you have one include file that includes another include file that eventually includes the original include file, and you forgot your header guards on sort of all throughout all the chain, yes, the compiler will just sort of sit there spinning as it keeps including this ever increasing list. So yeah, so that's why include guards are very important in your header files. All right. So how do we get around this sort of combinatorial explosion of includes? Oh, there was.
Suppose you have two free functions in two different files, both of which have the same namespace. Then how
So if you have two identically named functions in the same namespace in two different header files, how does it know which one to take? If you have only one include, basically what will happen is you'll probably get a compiler or a linker error. So if you include both of them at the same time, the compiler will complain because it'll see both of them and it'll say that there's a clash.
I'm not including it. I'm only including one. I don't really know that links onto the other one through the chain somehow.
Right. Well, I mean, so even if, so you're only including one, but if another one also implicitly includes it, the compiler will see both. And then it will have an issue. Even if for that particular compilation unit, you only have that one header file, probably someone else is using that other function in a different CC file. And then when you go to link, you'll have that name conflict, and the linker will complain that it's defined twice. So yeah, in that sort of situation, you probably get a compiler error or some sort of linker error, and it's just you shouldn't have the same function in the same namespace with the same signature defined twice. If there's a conflict between the two, even if you judiciously select out which headers you're using, you're going to run into a problem sooner or later. Yes.
When it comes to like header and forward headers, to my understanding, I may be completely wrong, but to my understanding, often the header for X file contains essentially the forward header for the same file. Right? This is very common. But I've seen in multiple cases now that we need to include both header and forward header. So why would that? Or am I mistaken somewhere?
So the regular header files usually contain the forward header files. And you're asking why would we need to include both in, for example, a CC file? Typically you wouldn't. I guess it's not too much of an issue if you have both of them because of the include guards on your forward header. So with the include guards, you'll only basically include the text once. So the first time it's encountered, the contents will be of the forward header will be included, and then the next time it will sort of not be included. But since the regular headers typically contain the forward header of the same name, most of the time in like a CC file, you would only need, if you needed both of them, you would only need to include the one header as opposed to both of them. All right. So forward headers, this is one of the ways we get around the fact that we have this large amount of includes. And so what we do in the forward header, we contain a forward declaration of the class. So this is just saying this class exists. It doesn't say anything about the contents of the class. And since we're not saying anything about the contents of the class, we don't have to include anything for headers for any of the member variables or the return values or the parameters, et cetera, as you would in a regular header. And then we also contain the owning pointer declarations. And for owning pointers, all we need is the forward declaration of the class and the owning pointer header file. So in forward headers, you really only have one include, and that's for the owning pointer include. And the owning pointer include is rather simple as well. And so when we have an actual class definition, so in our header file, our regular header file for another class, if all we're dealing with is storing owning pointers to a class, all we have to include in the headers is the forward headers. If we were storing the complete object, the C++ compiler wouldn't have to know the specifications of the entire object, which would mean including the regular header file. But since we're only storing the owning pointers, this means we only have to include the forward header file, which is where the owning pointers are defined. So by storing pointers as opposed to storing objects, we reduce the number of headers that we have to include in each file, and therefore we reduce the compilation time. And as many of you have learned, reducing compilation time in Rosetta is a laudable goal and helps everyone out. There is one drawback to storing owning pointers as opposed to storing objects, and that's the fact that by storing owning pointers, you now need to be explicit about your default and copy constructors, your assignment operators, and your destructors. The reason for this is the fact that when the C++ makes the default versions of these, it needs to know about the member variables, and the member variables are the owning pointers, and so it now needs to have more details about the owning pointers when it actually makes the default versions of these. So when you actually, so if you're not being explicit, if you're not saying, don't worry about the assignment operator, I'm going to be defining it in the CC file later. Every time it encounters a place where it needs a copy constructor, for example, it will try and make a default implementation. And in order to make that default implementation, in addition to knowing about the owning pointer, it needs to know details about what it's pointing to. And so it will complain about the fact that you've not included the header for the object that's being pointed to via the owning pointer. And so you'll see this occasionally where you'll have a file, a header file that you declare a class, and you'll get a compiler error that says, unknown class or ill-defined class, and it will say, yeah, this class that's being pointed to by an owning pointer, I don't know enough about it to work. And then, if you change a forward header to a regular header, all of a sudden the compiler is happy again. That change from a forward header to a regular header is not the way to fix that. What you really should be doing, and most of the times when you encounter that situation, you should be saying, oh, I'm just having an owning pointer in the class definition. I don't need the full header file. What's probably happening is I have an implicit copy constructor or an assignment operator or a destructor, and then I need to make an explicit version of that. You declare it in the header file and then define it in the CC file. And by moving that implicit declaration in the header file to an explicit one where you define it in the CC file, you only have to have the full header in the CC file. So, all right. So the other reason why you might want to store pointers is if you actually do want to share objects. And so sharing objects is very good. In certain situations, I guess Andrew was talking about the ramping mover, and there's various other types of movers, for example, like fast relax, where we take and we change certain shared objects. For example, if we change the repulsive weight on the score function. So there's sort of two ways you could go about doing this. So one is, so if you have one mover, it changes the weight on a score function and then invokes a bunch of submovers. So it either could go through each of those different submovers and then reset their score function to the new score function that has the changed weight. Or you could just share one score function between the fast relax mover and all of the submovers, change that weight once in that single score function, and then every mover that shares that score function would now see that changed and updated weight. And this is a little bit more elegant way of doing it, where you make a change once and it automatically propagates to everyone who needs that change. And so that's basically what the lab is right now. So the lab is going to ask you to make different classes, some with a shallow copy semantics, some with a deep copy semantics, and then do unit testing and observe the behavioral difference between the two different types of classes.